Hello everyone. Today we are going to talk about maximum and minimum values of a function. Now there is one word that captures the essence of both maximum and minimum. It is called extremum. So an extreme value can mean both maximum value and minimum value. And the plural of extremum is extrema. So in this lecture we are going to talk about extrema of a function of a real variable. Now this is a very interesting topic on its own, but the story has a twist. And the twist comes from mean-value theorem. So definitely we need to split this story into two parts. And today we are going to see the first part of the story of extrema. So let's start. Extrema, part 1. Let me start with a few words. So what I said is extremum. This can mean maximum or minimum. So sometimes, just to save some time, we'll just call extremum. So that can mean maximum or minimum. Okay, and some plural forms of these words. And this, if I have maximum, the plural of maximum is maxima, and the plural of minimum is minima, and the plural of extremum is extrema. Okay. All right. Now we all have some kind of notion of what a maximum or minimum means. So a maximum value is the highest value of the function, right? So let's take a function like this, x-axis, y-axis, and suppose we have the graph of a function like this. And let's say the domain of this function is the interval, closed interval a to b. Okay. Now if you look at the values, which value is the largest among all the values of this function? Yes, of course, this is f of b, right? So f of b is the highest, right? And we can call it maximum, right? But there are some other notion of maximum too. So for example, let's call this point C and this one D. Now let's just zoom at this point. Okay, so let's take a really tiny interval centered at C. Now if you look at this thing, this interval, and forget about everything and look at all the values, you will see f of C is the largest among them, right? So what it means is, if you forget about all the other value and just zoom in at C, so you just focus around C, then f of C is a maximum. So you call this kind of maximum a local maximum or a relative maximum. Okay, so f of C here is a local or relative maximum. And similarly, let's think about this point D. If you zoom in there, let's take a small interval containing D, and then if you look at all the values, you will see f of D is the smallest among them, right? It may not be the smallest in the whole domain, but it is the smallest if you just focus on that particular interval. Okay, you can actually narrow this interval, doesn't matter, but still it's going to be the smallest, right? So f of D, we call this a local or relative minimum of this function f. Okay, I need to actually change this graph a little bit. I didn't notice when I draw this thing, so let's just make it here. Okay. Now, what is the smallest value, the minimum value in the whole domain? Yes, of course, that is f of a, right? So we'll call f of a an absolute minimum or a global minimum because we are considering the entire domain. And f of b, that's the absolute maximum of this function, or the global maximum. Okay, so let me just list these things. F of b, this is the absolute or global maximum, and f of a, that is the absolute or global minimum of my function. So that's the idea. We are just going to play around with this idea all through this lecture. Okay, now we kind of showed what relative maximum, relative minimum, and absolute maximum, absolute minimum are, but we need to write this thing as a precise definition. So the next thing I'm going to do is to write a definition. Actually, write two definitions of them. Okay, so I have to erase this thing, although I actually need this thing. Anyway. So definition, this is absolute slash global extrema let f be a function with domain D. Okay, domain means the set of all inputs, and let C be a point or be an element of D. So what it means is that f of C is defined, i.e. f of C is defined. Okay, then f of C is the absolute maximum. Okay, so it will have two parts. It's the absolute let me also include global, absolute slash global maximum of f if what happens, the value at C is bigger or equal to every other values, right? If f of C is bigger or equal to f of x for all x in D. Okay, now notice you have to read this thing carefully. We have included equality here. Okay, it doesn't have to be strictly bigger than all the values. It can happen that it is equal to all the values. So still qualify. It is still qualifies to be global maximum. Okay, all right, now the other part of this story is what it is. F of C is sorry, I forgot, is the absolute slash global minimum of f if f of C. Now the situation changes. It is the smallest one, right? So f of C has to be less or equal to all other values. So f of c is less or equal to f of x for all x in D. Okay, so that's the definition of absolute or global maximum and minimum. Okay, so now the other part of the definition. So this is relative / local extrema. Okay. Let f be a function, just the same setup. With domain D, and let C be an element of D. Okay, that means f of c is defined, i.e. f of c is defined then f of c is, so two parts, a relative / local maximum of f if f of c is not bigger in the whole domain. It doesn't have to be bigger in the whole domain. It just has to be bigger in some interval containing the point c. If f of c is bigger or equals to f of x for all x near c. Okay, now this phrase x near c needs some clarification. I'm going to explain what x near c means in a minute. Okay, and this is a relative / local minimum of f if the opposite happens. F of c is less or equal to f of x for all x near c. Okay. Now what does the near c mean? So that's when I actually need to graph the picture one more time. I'm going to graph the picture here and I will finish the sentence over there. Okay, so we had this situation at the beginning. So at C we had a maximum, local maximum, right? So what he said, we need to take an interval that contains my C, and then we are comparing all the outputs that's coming from this interval. Okay, so if this is my x, then f of x is going to be this much, and that f of x is definitely less than f of c. And then if x is coming from here, then this is going to be my f of x, and that f of x is also less than or equal to f of c, right? So what we need an interval containing c, but that interval should lie inside the domain of the function. It cannot go outside of the domain. Okay, all right, so where x is near c means the x is in some interval let's call it AB, such that AB contains C and is contained in the domain of F. Okay, so for this problem, let's just change these names. Let's call this one to be P, this is Q. Okay, so the whole domain is P to Q, and we took this interval A to B. Now this interval contains my point C. Okay, and then we are taking all the x values which are contained in this interval A to B. Okay, so f of c is a local maximum if f of c is bigger or equal to f of x for all x in this interval. Okay. Now this interval doesn't have to be fixed. You can actually narrow this interval as much as you want. So you can take an interval like this. It still will work. Okay, you can keep shrinking this thing. All right, now one question: why? This is f of q, okay? Why this guy is not a local maximum? Or why f of p is not a local minimum? That we need to understand. So, in order for q to be a local maximum, we need to take points which are near q, right? And how do we take those points? We take some interval centering at q, right? So now if I take an interval there, but notice this interval has to be contained in the domain, but those parts are outside of the domain, right? Right? So we can actually compare all the x values which are near q. They're limited there. Okay, and the same thing happens at p. So at p, suppose you take an interval, right? See all those numbers on the left side. These are bad numbers because they are not in the domain. Okay, so we need to fit an interval that contains my point C, and that interval should be contained inside the whole domain. That's the restriction. Okay, all right, so a couple of remarks here. So first thing you should notice, at the definition of absolute or global maximum or minimum, we said f of c is the absolute maximum or the absolute minimum. And then when we talk about relative or local maximum and minimum, we said a local maximum, a local minimum, right? So you see the difference in the articles, and why are they? Because if a function has a global maximum, that has to be unique. We cannot have two different global maximum. If a function has a global minimum, that has to be unique. Okay? But a function can have more than one local maximum. It can have more than one local minimum. That's perfectly okay. All right, so then first remark is about global extrema. So remarks. If f has a okay, let me just, if f has an absolute maximum, then it is unique. Okay, and similarly, if f has an absolute minimum, then it is also unique. That's why we say the absolute minimum, the absolute maximum. Okay, but number 3, a function can have more than one local maximum. It definitely can. And also it can have more than one local minimum. And an example of that is this. Okay, suppose you have this function f, and now let's say this one c, let's call this d, e, we have f as the name of our function, so what should I call it? Say m, let's call this n. Okay, all right. So notice this function has 1, 2, 3 local maximums, right? And also it has 2 local minimums. Okay, so local maximum and local minimum, they are not unique. Okay, all right, but the most important observation here is this. Look at this thing. What is this? This is a local minimum, right? And what is that? That is a local maximum. But notice this local minimum is bigger than the local maximum. That's totally okay, because when we talk about local maximum or local minimum, we are just concerned about what happens near that point. We don't worry what happens really far from that point, right? So d, f of d is a local minimum. What it means is we take a tiny interval containing d, and we compare the values of all the inputs coming from that interval, right? And among all the values, f of d is the smallest one. That's why it is called a local minimum. That's it. But this f of d is certainly bigger than f of n, right? But f of n is also a local maximum, right? If you take a tiny interval containing n, then you will see f of n is bigger than all the outputs coming from that interval. Okay, so this is the last remark here. Number 5, a local minimum can be bigger than a local maximum. Okay, and this is an example of that. Does it make sense? So now that we know the definition of local and absolute extrema, let's solve a problem, okay? This is an exercise. Find the local and global extrema of the following function. Okay, and this function is given actually by a graph, so it's not just a function, it's actually the graph of the function. So let's start like this. So from here I will go all the way up to there, and let's come up to here, and then I will go up like this, down like this. Okay, then I'll go straight. All right, it's good enough. Okay, let's just add one more thing. So okay, I want to make this absolute maximum. All right, so let's call this point A, this is B, this is C, this is D. Oh, by the way, this function is given by F, okay? D, and this is E. And again, the same problem. The function is named after F, so we cannot call this point F. So let's call this point K. Okay, let's call this one L, and let's call the last one to be M. Okay. That's the graph of my function. Okay. Now I'm going to ask a question, and you guys should actually answer those questions. Although there is no way I can check whether you are working on this problem, but I will pretend you are doing. Okay. The first question is, list all the local maximum of this function. Did you get one? Yes, of course. F of D is a local max, right? Okay, very good. By the way, what happened to F of B? Did you think F of B is a local max? No, it's not. And why it's not? Let's take an interval centered at B. Okay? All right. Now, what is F of B? This is F of B, right? This much is F of B. Okay? Now, if F of B is a local max, what happens if I take any input from this interval, the corresponding output has to be less than F of B. That's the definition of local max, right? All right. So, let's take an input, let's say this one, very close to B, but not B, from the left side of B, okay? Now, what is the output? It is there, right? And if you look at that output, that's not less than F of B. That's actually bigger than F of B, right? So what is the definition of local max? Local max says you take that point and then you take an interval, then all the outputs coming from this interval has to be less than this specific value, but that's not happening for B. So F of B does not qualify to be a local maximum. Okay? Alright, so F of D is a local max, then what else? Is that all? No, it's not, right? If you look at K, so let's take an interval around K. Okay? And this much is F of K, right? Okay, so if you are plugging in any points from the left side of K, you see those values are less than F of K. Okay, so it's good. And if you are plugging any value from the right side of K, then what happens? All those values are exactly equal to F of K. That's also good. If you look at the definition says it can be bigger than or equal. It includes both possibilities. It doesn't have to be strictly bigger than. So F of K actually qualifies to be a local max, right? What about F of L? That's also a local max, right? So if you take an interval here, on the left side, if you plug in any value, the corresponding outputs are exactly equal to F of L. That's fine. And then if you're plugging in anything from the right side, those values are like this, right? But they are all shorter than F of L. So F of L is actually bigger than all the outputs coming from this interval, okay? So F of K is also a local maximum. F of L is also a local maximum, right? Are those all? Can we have more? Yes, we can. Actually, notice if we take any point in between K and L, let's say I take this one, okay? and then if I take an interval, on the left side the outputs are exactly equal to that, on the right side the outputs are also exactly equal to that. So all the numbers between k and l, they will give you local maximum. Okay, by the way, I just noticed I made a grammatical mistake here. It's not a grammatical mistake, I said local maximums, right? It's the plural of maximum is maxima, so I'm going to erase that. This is Latin and I have no knowledge of Latin. Okay, so f of d is a local maximum, and what else? And f of x for all let me write this way, f of x whenever x is coming from this interval between k and l. Okay, these are all the local maxima. Does it make sense? Okay, now what are the local minima? Of course, f of c, right? Good. What else? F of e, right? So f of c is a local minima, f of e is a local minima. What else? Can f of k be a local minima? No, because if you take anything on the left side, those values are not bigger than or equal to f of k, right? So they are actually less than that, so less than f of k, so that will not qualify. What about f of l? No, because what? If you are taking any point from the right side, those values are strictly less than f of l, right? So f of l will be a local minimum if f of l is the smallest, or at least equal. But on those intervals, you see, those outputs are actually smaller than f of l. So f of l fails, f of k fails. Now what happens between k and l? They are good, right? So for example, I take this number, and then on the left side, if I take any input, the corresponding output is exactly equal to that. But that's fine, okay? And the same happens on the other side, right? So f of c, f of e, and f of x, whenever x is now strictly between k and l. Okay? Alright, so now we have local maxima, local minima, and then we are going to figure out global maxima, maximum, and global minimum. So number 3 is global maximum. Now what is going to be the highest among all the values? F of m, right? I deliberately made this longer so that this guy is not the global maximum. Okay, yes, f of m. And what is the global minimum? F of a, right? That's the smallest. All right, so what have we learned so far? We have learned the definition of local and global extrema, and we have figured out local and global extrema from a graph, okay? But the problem is, how are we going to figure out this local max or mean or global max or mean when there is no graph, when we have just the formula of the function? Okay. In reality, it is really hard to draw the graph of a function, and actually we need to know these values to sketch the graph of the function. It's the other way around. Okay? So this is a big problem. And why it's a big problem? Because we always want to know what is going to be the maximum or minimum. We want to maximize our profit. We want to maximize our happiness, right? We want to minimize our sadness. We want to minimize our losses, right? So we always want to know what are those extreme values, okay? But there is a bigger question here. Is it always guaranteed that your function is going to have a global maximum or a global minimum? No, it's not. Okay. But there is a nice situation where you are guaranteed to have a global maximum and also a global minimum all the time. And that's the next content. It is called the extreme value theorem, EVT. This is another very important theorem in calculus. So theorem extreme value theorem, and in short we call it just EVT for short. Okay, so what does it say? It says that if a function is continuous on a closed bounded interval, then it is guaranteed to have an absolute maximum and an absolute minimum. Okay, so let f be a continuous function defined, let's not put the word defined, let f be a continuous function on a closed bounded interval. Okay. Now you need to actually highlight several things. First of all, it is continuous. That's very important. If your function is not continuous, this is not guaranteed. And the next thing is closed. That's one thing, but also very important thing is bounded. Okay, so the domain has to be closed and bounded. It cannot go to infinity or negative infinity. Going to infinity or negative infinity, that's unbounded. Okay, I'm going to show you examples where things actually fall apart. Okay, let f be a continuous function on a closed bounded interval. Then f attains both absolute or global maximum and absolute minimum. Okay. This is a very powerful theorem, and that's actually at the heart of many things that we do. But unfortunately, we are not going to learn the proof of this thing. It will require some deeper things, completeness axiom of real numbers. All right, now just let me give you some illustrations. So it can happen that your function, let's say this is your domain, starting at A, ending at B. It's a closed interval and it's bounded. Okay, and your function can look like this. Let's say, okay, and here you see this guy. This is C, so f of C is your global max. Let's call this one D, and f of D is your global min. Okay, I'm actually used to both terminology, absolute max and global max. So both are fine, you can use any time. All right, so f of C is the global max, and then f of D, this is global min. By the way, if you look at this, these are actually, these are also local max. F of C is also local max. This is also local min. Okay, so it can happen your local max and global max, they are same. Local min and global min, they are same. It's a very common story. But here we are mostly focused about global max and global min. Okay, we want to know the highest and the lowest that happens in the whole domain. Alright, so that's one scenario, and then we can have this scenario. We can have a function like this. Okay. A to B, that's a close bounded interval. My function is continuous and it attains a global max. What's the global max? Let's say this point is C, so f of C is the global max. Okay, and what is the global min? It is f of A and also f of B, right? They have the same height. So global max, this is f of C, global min, this is f of A, which is the same thing as f of B. Okay, so I'm reminding you one more time, what do you need? You need continuity, number one. Then you need the domain to be closed and bounded. Okay, three things. If any of those three things fall apart, this is not guaranteed anymore. Okay. So I'll give you two more illustrations. And then I'll give you situations where it falls apart. So number three, we can have an interval like this, A to B, and your function can be like this. Okay, definitely it's a continuous function and your domain is closed and bounded, and global max is f of A, global min is f of B. Okay, and the last one is the most obvious one. What is the most obvious scenario? It's a straight line, horizontal line, it's a constant line. Okay. Alright, so what is the global max? This is f of x for all x, right? Every output has the same value. And global min is also the same thing. For all x between A and B. Okay? Alright, so these are possible ways that you can see a continuous function to have both global max and global min. Alright, now this is one of the situations when we tend to misread the theorem. You're going to see this in a moment, but it will show up in two more places today. Reading math carefully is one of the most important things, and you will see it right now. So example, for each of the following functions, find its global extrema. So that means find its global maximum and minimum. Okay, if the global max or the global min does not exist, explain why it does not contradict our theorem. Okay, explain why does not contradict the extreme value theorem. Okay, so the first example is something that you have already seen today. So this is the domain and it is closed and bounded. Very good. And okay, so that's my function f. Now what is the global max? Let's give this point a name. Let's call this C, right? Is f of C the global max? No, because if you take any input from the left of C, right? Let's say I take this one, okay? Then the corresponding output is here, right? So that output is much bigger than f of C. So f of C is not the greatest among all the outputs, right? Okay, so f of C will not be global max. It's not even a local max. All right. Then what is the global max? What is the highest that it can go? So here is the thing. Let's take some point which is closer to C, okay, but bigger than this blue point. Let's take it, this one, red. Then what is the corresponding value? It's there, right? Okay. Or if you want, you can actually draw it there. And the blue one was here, right? Okay. These are all outputs of my function. But what is the highest? What is the largest among all of them? There is no largest value. That's the thing. There is a limit of this thing, right? As your x approaches C from the left side, your f of x approaches to a limit. But notice that's not the value of the function. So your function or our function never attains that value. It is there as a limit, but my function cannot grab that value, never achieves that value. It's like a fantasy. Okay? Alright, so global max does not exist. DNE, okay, does not exist. And what is the global mean? Definitely it's f of b, right? Okay. And why doesn't it contradict the extreme value theorem? Extreme value theorem says my function has to have both global max and global mean. But here I have global mean, but I don't have a global max. Why is it happening? Something went wrong. What was that? My function was not continuous. Exactly, that was the very first condition for extreme value theorem. Function has to be continuous. That's number one. Okay, and it breaks there. That condition. Okay, it does not contradict EVT since f is not continuous. So when we say not continuous, we mean in the whole domain. So in the extreme value theorem, when it says it is continuous, that means it is continuous at every point on the domain. Okay. So this is not continuous. This does not contradict extreme value theorem because f is not continuous in the whole domain. Actually, it is not continuous at C, but that's enough. Okay. All right. The next example is this. Our function is like this. It's like the 1 over x function. Okay. and domain is what is the domain? It's a to infinity, right? Okay. Now what is the global max? Of course it is f of a, right? That's the highest one. What is the global mean? It does not exist. Okay. Why? As you keep going and going towards infinity, these values are shrinking and shrinking. They are getting towards zero, right? But it never becomes zero. The whole point is whether my function achieves that value as an output. Okay? There is no input here that you plug in so that your output is going to be zero. No, it does not happen. It does not achieve that value. Okay? So no global mean. Now once again, it's not the conclusion of the extreme value theorem, right? Extreme value theorem says your function has to have both global max and global mean. Now you are having one, you are losing the other one. And why are you losing the other one? Why doesn't it contradict? My function is continuous, right? It's better than this one, the previous one, right? Then why is it breaking? Because the domain is not bounded, right? A to infinity, that's unbounded, it's infinite length, right? It does not contradict EVT, since the domain is unbounded. Okay, the opposite of bounded is unbounded. Okay, does it make sense? All right, now the next thing we're going to do is this. Let's extend this a little bit. Okay, it's something like the log function. Let's say it starts here, let's call this b, and it goes like this. That's my function f. Okay, so the domain, what is the domain in this case? This is 0. Okay, it does not have any output at 0. Also, it does not have any output for any negative inputs, right? So the domain starts after 0, so 0 up to this point b. Okay, all right. Now what is the global max? It is f of b, right? And what is f of b? It is 0. Right? So global max is 0. And what is the global mean? There is no global mean, because as my inputs are getting closer and closer to 0, outputs are becoming smaller and smaller and smaller. Okay, there is not one single value that you can say, okay, that's the lowest, right? Something like frustration, you know, it goes down and down and down, it never ends. Okay, all right, so global mean does not exist. Okay. And the question is, why doesn't it contradict EVT? It does not contradict extreme value theorem, since what should be the reason? My function is continuous, but domain is also bounded, right? But something is happening. What is it? This is not a closed interval. Not a closed interval. That's the thing, right? We had three requirements. Function has to be continuous, domain has to be both closed and bounded. Okay, so in the previous problem it was not bounded, that was the issue. Here it is bounded but it's not closed. Okay, since the domain is not closed. Okay, so there you go. These are three situations where three hypotheses of the extreme value theorem can fall apart, and therefore there is no guarantee for you to have both global max and global mean. By the way, you have to understand this thing. So extreme value theorem does not say anything what happens in these cases, right? And still sometimes you have a global max, sometimes you have a global mean, right? Or I mean you can have both. Okay, so when your function is not continuous, or if your function is continuous but the domain is not closed or domain is not bounded, even then you can have global max or global mean, or maybe both, right? But there is no single rule for that. There are some analysis to figure that out, but that's coming next. Okay, all right, but the hope is extreme value theorem says as long as your function is continuous and your domain is closed and bounded, you are definitely guaranteed to have one global max, I mean there is always one global max, and global mean. Okay, so that's the hope. But the problem of that is what? The problem of that is extreme value theorem tells you that there is the maximum and the minimum. But how do you figure that out? Where does it lie? That's the hardest part. Okay, so we know that there should be a maximum, global maximum and global minimum, but how are we going to figure that out? Where is that maximum? Okay, what should I do to maximize my profit? Right, so it's that kind of question. So extreme value theorem is, again, it is one kind of existential theorem. It says that it exists, but it does not say where it exists. So we need to actually investigate through that. Okay, all right, now this is the question. So how to locate the global max and global mean of a function that is continuous on a close bounded interval. Okay. Do you understand the question? So extreme value theorem says if your function is continuous and domain is closed and bounded, there will be global max, global mean, right? But the question is, how am I going to locate those global max and global mean? Okay. And the idea is very simple. Let me just graph one picture and you notice that immediately. So suppose I have this continuous function, okay, yeah, on this close bounded interval, right? Now where is the global max? This is the global max, right? F of b. And what is the global mean? f of d, right? Okay. Now notice all we had to do is basically compare these values, right? So global max should be either one of the values at the endpoints or one of your local maxima, right? And your global mean should be one of those values at the endpoints or one of your local minima. Okay? All right. So it is actually, the idea here is this idea or the solution is this: compare the values at the endpoints with the local extrema. Okay, and the one that is the biggest among all these values is the global max, and the one that is the smallest among all those values is the global mean. Okay, then the largest of these values is the global max, and the smallest of these values is the global mean. There you go. Okay. So in order to get the local global max or global mean, all we need to do is we need to do what? Locate where we have the local max or local mean, because the endpoints are pretty easy, right? You just plug in those values. So suppose your function is defined on the interval 0 to 5. So you just plug in 0 and plug in 5. Those are easy to get. But how do you know at what points does your function have local max or local mean, right? So actually this question boils down to the question of locating the local max and local mean. That's the next question. Okay, so you're gradually unwinding this situation of global max, global mean, and it's a very interesting story. All right, so the new question. New question is this: how to locate the local max and local mean, or in one word, how to locate the local extrema. Okay. Once you know how to locate your local extrema, then you're done. You just get those numbers, plug in those numbers to the function, and you evaluate your function at the endpoints, and then you just compare the values. The largest one is the global max, smallest one is the global mean. Okay? But how are you going to do that? How are you going to locate the local extrema? There, something interesting happens. All right, so suppose you have a function like this. You have a local maxima here and a local minima there, right? So these are local extrema. If you look at the tangent, if you look at the tangents there, what happens to the tangent at that point C? It's a horizontal tangent, right? So that means f prime of C is 0, right? And at D, the same thing. If you just slide a straight line, and then whenever it reaches at this point df of D, then that also becomes horizontal. So that means f prime of D is also 0, right? So that gives you some geometric hint where to look at. And some guy did, and he proved an interesting criteria. It's called Fermat's theorem. Okay, now Fermat is a really big shot. He did many great things, but this guy was notorious. He just wrote his discoveries in the margin of the textbook. Yeah, and people actually figure out his claims, and they all turned to be true except one, and that one took 300 years for all mathematicians to actually solve that. And you can watch that. There's a documentary on that. It's a really fascinating story. You can, it's a BBC documentary, and you can find it many places in internet for free. All right, so let's go back to this Fermat's identification. So what did Fermat do? So Fermat's theorem. Fermat's theorem. If f has a local extrema at x equals to c, and if f is differentiable at c, i.e. if f prime of c exists, then what happens, this thing will definitely happen, that the derivative must vanish. Okay, then f prime of c equals to 0. And proof of this is really simple. We can prove this. I'm actually going to prove one of them. Okay, so local extrema can mean both local maxima and minima, right? And the proof works almost the same for both cases. So I will just prove this. We'll do this only for local maxima. Okay. All right. Now f has a local maxima at c, right? So the picture should look like this. Something like this, right? Around c. Okay. And since this is a local maxima, if I take an interval centering at c, then what happens? All the outputs are actually less than f of c, right? So if x is coming from here, then f of x is less than f of c, right? Okay. All right. So suppose let f of c be a local maxima of f. Okay. All right. Then what happens? F of c plus h is less or equals to f of c whenever h is very small. Okay. So what I mean by that is, suppose h is a positive number, right? Then c plus h is where? Then this is c plus h, right? But since f of c is a local max, f of c plus h is definitely going to be less than f of c, or equal. Okay. And if so, this is if h is positive, but also h can be negative, right? So this is c plus h. Here h is negative, so c plus h is less than c. But again, on this side, since f of c is local max, so f of c plus h should be less than f of c, right? Okay. But that's the key. So that means what? Which means f of c plus h minus f of c is less or equals to 0, right? So I subtracted f of c from both sides, where h is very small. Where okay, now we'll just use the difference quotient and take the limit. Okay, now two cases. Case 1, if h is positive, then if we divide this inequality by h, what will happen? The inequality sign will remain the same, right? Then f of c plus h minus f of c over h, this is less or equal to 0, right? Now we can take a limit as h approaches 0. So limit of this difference quotient as h approaches 0, but notice here h is positive, so h approaches 0 from the right side, and a limit of this is less or equal to limit of 0, which is just 0. Okay, now what did Fermat's theorem say? It says that as an hypothesis it had f prime of c exists, right? So f prime of c exists, that means this limit of the difference quotient as h approaches 0, that exists. Now if a limit at a point exists, that means the left hand limit and right hand limit, they both exist and they both are equal, and they are equal to the same limit, right? So that means this limit on the left side, this is none other than the derivative of f at c. Okay, so from here we get that f prime of c is less or equal to 0. Okay? Alright, now let's go to this other case, case 2. Now in this case h will be negative, so we are talking about this point, c plus h is now on the left side of c, right? If h is negative, then now we are going to divide this both sides of this inequality by h, but since h is negative, it flips the inequality, right? So f of c plus h minus f of c over h is now going to be bigger or equal to 0. Okay. Just like the previous case, now we can take a limit as h approaches 0, but our h is negative, so this limit will approach 0 from the left, right? So this means limit of the difference quotient f of c plus h minus f of c over h as h approaches 0 from the left, this is positive or 0. Okay, and just like the previous case, since f prime of c exists, that is exactly equal to this limit, so that means f prime of c is bigger or equal to 0. And now we're done. How? Now if h is positive, then it says that f prime of c is less or equal to 0, right? What does it mean? It means that it cannot be positive. And if h is negative, then it says that f prime of c cannot be negative. Now what number is neither positive nor negative? It is just 0, right? So f prime of c has just one choice, it can be 0, because if f prime of c is 0, then it will satisfy this inequality and also satisfy this inequality. It will satisfy both inequalities only if f prime of c is 0, right? So we get this, therefore prime of c equal to 0. Okay, that's the end of the proof. And we can do the same process for local minima. This inequality signs will just flip. This will be positive, but then you'll run the same argument and then it will give you f prime of c equal to 0. Okay, so Fermat gave a criteria. If a function has a local maxima or local minima at a point, and if the function is differentiable at that point, then it must have derivative 0 at that point. Okay, but this is another very important part to notice. Actually, I regret that I erased that sentence. Okay, I'm just telling that. So what did Fermat say? Fermat said if two things happen. then a third thing will happen. What are the two things? Your function has to have a local extrema at C, and then your function has to be differentiable at C. Those are the two conditions. Okay, those are two hypotheses. So Pharma says if those two hypotheses are satisfied, then you will have the conclusion. What is the conclusion? It says then f prime of C equals to 0. But it does not say that if f prime of C equals to 0, then your function will have a local minima or a local maxima. That's not what Pharma is saying. Okay, this is a common mistake. People tend to overread the statements. So let me just give you an example. So I will just make a cautionary remark. So caution, the converse of Pharma is not true. So what it means, i.e., if f prime of C equals to 0, then f does not necessarily have a local extrema, which can mean both maxima and minima, right? Extremum actually at x equals to C. And what can be an example? Example is so simple. Actually, this is really fascinating. In many cases, the counter examples are so simple to get. This is one of the cases. Example. Actually, this example will show up in next few lectures. In concavity, that's what I mean. This one also has a very interesting property. All right, so let f of x be equals to x cubed. Okay, then f prime of x equals to 3x squared, right? And what do we need? We need f prime of c equal to 0. So we need to set our first derivative equal to 0. That will give us 3x squared equal to 0. That means what? X squared equal to 0. We can divide both sides by 3, and then we can take a square root, then we get x equal to 0, right? So this function f of x equal to x cubed will have its derivative 0 at x equal to 0. Now, will this function have a local maxima or a local minimum at 0? No, it will not have either one. So here is the picture of that. X cubed looks like this. No, it's not true. So it goes like this and then goes like that. Okay, so this is x cubed. Now notice we are focusing at point x equal to 0. So this is 0, right? And now for it to be a local maximum, what do we need? We need to take a tiny interval centered at that point, right? So let's take this interval. Okay. And if f of 0 is a local maximum, then what happens? Then f of 0 has to be bigger than all the other outputs, right? Okay, now here's the thing. Let's take this output. What is that going to be? It's something positive, right? It's here. So it's there. But what is f of 0? F of 0 is just 0. Okay? And no matter how small you make your intervals, those values which are on the right side of 0, they will always be positive once you cube them. And therefore those values are definitely bigger than f of 0. So f of 0 does not qualify to be a local maximum. Okay? And similarly, it does not qualify to be a local minimum. For example, take this point from here, then the output is what? This much, negative, right? So this, if f of 0 is a local minimum, it has to be the minimum among all the outputs coming from that interval, right? But see, this input will make an output which is less than f of 0. And we can actually shrink these intervals. Now let's take this as your input, then output is going to be somewhere here. Okay? So there will always be values close to 0 that will make outputs less than 0 and bigger than 0. So that means f of 0 is neither a local maximum nor a local minimum. Okay? So from the picture, or actually the graph, below, what do we have? We see that f of 0 is not a local extremum. Okay? So once again, what does Pharma say? Pharma says if your function has a local extremum and if your function is differentiable at that point, then the derivative must be 0. But Pharma does not say the opposite. What is the opposite? The opposite is if the derivative vanishes at a point, then the function has a local extrema at that point, which is not true. And that's a counter example. Okay, you always need to remember this. This is a very important example. All right, now where we were actually. So before this, we were talking about locating local maximum and local minimum, right? Or actually, that came from the question: how can we locate the global extremum, right? And then it turned out that if we have a closed bounded interval, then by EVT, extreme value theorem, we are always guaranteed to have a global maximum and a global minimum. Then the question is, how can we figure those points out, right? And it turns out that we just need to compare the values at the endpoints with the values where we have local extrema. Okay, so that whole question actually turned into the question of finding or locating the local extrema, and Pharma's theorem gives a very good answer to that. But his answer has also one limitation. What is it? So what does Pharma say? One more time. Pharma says my function has to be differentiable, right? Now what happens if my function is not differentiable? Will my function have a local maxima or a local minima? Yes, it can. So remark, notice a function f can have a local extremum at x equals to c, even if f prime of c does not exist. This is another very important thing to remember. Can anyone give an example of that? This example, I'll give two examples. So let's take f of x equals to absolute value of x, right? And this is the graph. And notice f of 0 is actually a local minimum, because if you take any interval centering at 0, then f of 0 has the lowest output, right? All the outputs are bigger than 0, right? Then f of 0 is a local minimum but what is f prime of 0? Does it have a derivative at 0? No, because it has two tangent directions, right? If you're coming from the right side, then this is going to be your tangent. If you're coming from the left side, this is going to be your tangent. So it does not have a derivative, but f prime 0 does not exist. Okay, so this is actually a very important part of the whole picture. So what is the whole picture? The whole picture is if a function has a local extremum at a given point, then basically two things can happen. One is if the function is differentiable, then the derivative must vanish. And the other thing is function is not differentiable. Okay, so there are two things, and actually that's the definition of what we call critical numbers. Okay, so the next thing is going to be the definition of critical numbers, but before we go to that definition, again another cautionary remark. So caution, now what did he say here? So he said that a function can have a local extremum even if the derivative does not exist. But once again, it's always very slippery, because these are all logic. So what's happening, we're giving an example here where we have a local extremum, right? But derivative does not exist. But don't make this mistake. It does not say that if derivative does not exist, it's always going to be a local maximum or a local minimum. That's not what it is saying. Okay, so caution, if prime of c does not exist, okay, so sorry, notice if prime of c does not exist does not mean that f of c is a local extremum. Okay, and an example of that is it's pretty easy actually to give an example geometrically. Okay, so let's take this this part. Let's take f of x equals to x. Okay, so f of x equals to x if x is greater or equal to 0, and then on this side let's take this to be x over 10 if x is negative. Okay, so here it's at 1, this is 0.1, so it should be like this. Okay. Then what happens? F prime of 0 does not exist, right? Because we have two different tangent directions. It's a corner. But if you look at this point 0, it's not even a local maxima or minima. It's just like x cubed. I have erased x cubed. Okay, if you take interval around this point 0, then what happens? If you take any input from the right side, they will be bigger than f of 0. So that means f of 0 cannot be a local maximum. And now if you take any input from the left side, they will be less than f of 0. So that means f of 0 cannot be a local minimum even. Okay, so it cannot be neither one. I mean, it cannot be any one of those. Okay, so but f of 0 is neither a local maximum nor a local minimum. Okay. All right, so let's go back to the story of locating the local extrema. So what we have figured out from Fermat's theorem and this observation, that if a function has a local extremum at a point, then either the derivative vanishes or derivative does not exist. Okay, so that's a very important criteria, and so we call those points as critical numbers of the function. Okay, but the definition has one subtle point. So I'm going to write this definition slightly differently than the textbook. So this is how it is, what it is, definition, critical numbers. Let f be a function then x equal to c is called a critical number of f if two things happen. First, and most often actually we forget the first criteria, that's why I'm excluding that. If number one is f of c is defined, your function has to be defined at those points. Critical numbers are points from the domain, okay, i.e. c is in the domain of f. Okay, so that's number one. And what is number two? Number two is f prime of c equals to 0 or f prime of c does not exist. Okay, all right, and I want to write this here even though I mentioned these things. Notice after the Fermat's theorem we saw what? We saw f of x equal to x cubed, that vanishes at 0 even though f of 0 is not a local extremum, right? And here we have this example where my function is not differentiable at 0 even though it's not a local extremum, right? So that means what? That means a critical number does not guarantee that the function will have a local extremum at that point. Okay, it can be neither one. Okay, remark, if x equal to c is a critical number, number of f, then it can happen how should I write this? If x equal to c is the critical number of f, then f of c, okay, yeah, here it is, then f of c is not necessarily a local extremum of f. Okay, an example of that was x cubed at 0 and then this one. Okay, in both cases x equal to 0 is a critical number, but f of 0 is neither local maximum nor local minimum. Okay, all right, so now actually we are getting towards the calculation part. Okay, so I've explained many things and then we went through many different directions to sort out what to do. Okay, now we know what to do. Now the goal is to look at the critical numbers. Okay, all right, before we go and figure out some global extrema, let me just calculate some critical numbers of some functions. Okay, that will give some practice. So example, For each of the following functions, find its critical numbers. And now I need to look at my notes for the function. What is it? F of x equals to x squared minus x minus ln x. Okay. So that's my function, and I want to figure out its critical numbers, right? Solution. So first we need to notice, if you look at this function, what's its domain? It's any positive number, right? 0 to infinity. And x squared minus x, that's a polynomial, and natural log, x squared minus x is a polynomial, it's differentiable everywhere, and natural log is differentiable from 0 to infinity, and so this whole function is differentiable everywhere on its domain, which is 0 to infinity, okay? So, the critical number part definition had two parts, right? So f of c is defined, that's one, but in the next part we have two cases, f prime of c equal to 0 or f prime of c does not exist. But here the function is differentiable everywhere on the domain, so we just need to think about this part, f prime of c equal to 0. Okay, so first we need to figure out the first derivative, f prime of x, which is going to be what, 2x minus 1 minus, what is the derivative of natural log of x? 1 over x. Okay, so that's my function. Let me just simplify this thing. So what do I have? I have x at the bottom, so this is 2x squared minus x minus 1. Okay, and if I factor that out, what do I get? Prime of x equals to, this is going to be 2x squared minus 2x plus x minus 1 over x. So I can factor out 2x from the first two terms. This is x minus 1. Then from the next two terms I can just factor out 1. So this is x minus 1 over x. So this is x minus 1 times 2x plus 1 over x. Okay? Now, f prime of x equals to 0. When is this guy 0? This is a fraction, right? A fraction is 0 when the numerator is 0, right? So that means x minus 1 times 2x plus 1 equals to 0, right? So that means x minus 1 equals to 0 and 2x minus 1 equals to, so that means x equals to negative 1/2 and 1. Okay? And when does this function fail to exist? F prime of x, if x equal to 0, right? And f prime of x does not exist if x equal to 0, right? Okay, so what are my candidates? Negative 1/2, 0, and 1. Oh, I always erase the important part right when I need it. Okay, so what is the very first thing in the definition of critical numbers? Those numbers have to lie in the domain of the function, right? Okay, now what is the domain of this function? 0 to infinity, excluding 0. Okay, so this guy is not contained in the domain. Negative 1/2 is also not contained in the domain. Therefore, the only critical number for this function is x equals to 1. Okay, all right. Since the domain of f is 0 to infinity, the only critical number of f is x equals to 1. Okay, that's how we figure out critical numbers. Okay, now I'm going to do one simple problem after this. I mean, this is also simple, but something pretty obvious. So let's say now f of x equals to some absolute value function. We have seen absolute value, just to remind you. Let's say f of x equals to absolute value of 2x minus 1. Okay. So we need to find its derivative and see where it vanishes or where it does not exist. Okay. So notice absolute value functions, we can write them as a piecewise defined function, right? So what is it? This guy is 2x minus 1 if x is bigger or equal to 1/2, and negative times 2x minus 1, which is negative 2x plus 1 if x is less than 1/2 or equal to. Okay. If you look at the graph, this is the graph, this is 1/2, and it goes like this, that. Okay. And once you know the graph, we can actually get the derivative of this. Hence, prime of x. This is, okay, so we'll split this in 3 cases. First of all, notice if x equals to 1/2, then my function has a corner. So derivative does not exist at that point. Okay, so if x equals to 1/2, it does not exist. Now if x is bigger than 1/2, then this is basically this straight line, which is given by this equation, this polynomial 2x minus 1, and the derivative of that is this 2. So this is 2 if x is bigger than 1/2, and when x is less than 1/2, it is given by this polynomial, negative 2x plus 1, and the derivative of that is negative 2. So it's less than 1/2. Okay. Now tell me, where does the derivative vanish? Nowhere. And where does it fail to exist? At 1/2, right? So that's the only critical number. I notice 1/2 is in the domain of this function, so it's fine. And therefore, the only critical number of f is x equals to 1/2. Okay. I'll find critical numbers for one more function, and then we'll do one very simple problem, and that will be the end of this lecture. So number 3rd, what is this function? F of x equals to x to the power 4 over 5 times x minus 4 whole square. So that's my function. We need to find its critical numbers. So always we need to start with the derivative, and here my function is a product of 2 other functions, right? So you need to use the product rule. So first, this is derivative of x to the 4 over 5 times x minus 4 whole square, plus now we keep x to the 4 fixed, and then we differentiate x minus 4 whole square, right? And here we have to apply the power rule, so this is going to be 4/5 x to the power 4/5 minus 1, so negative 1/5, and this is x minus 4 whole square, it will remain the same, and this is x to the power 4/5, and here we need to apply the chain rule, x minus 4 whole square, so this is going to be 2 times x minus 4, and then you differentiate x minus 4, which is just 1. So that's the derivative. Okay? Now we need to simplify this thing a little bit. So f prime of x equals to, what is this thing? This is 4 times x minus 4 whole square, and at the bottom I have 5 times x to the 1/5, and this one is 2 times x to the 4/5 times x minus 4. Okay. It's hard to solve for 0 at this moment, but it will be much easier if we just add these two fractions. Alright, so we need to have common denominators, right? So this is 4 times x minus 4 whole square, 5 times x to the power 1/5. So we need to multiply top and bottom by 5x to the power 1/5, right? But then on the top I will have what? 5 times 2, which is 10. X to the power 1/5 times x to the power 4/5 is just x. X times x minus 4. Okay, so now I have common denominator, so we can just add the numerator to get the summations. So 4 times x minus 4 whole square plus 10 x times x minus 4 over 5 times x to the power 1/5. Okay, can we factor out anything from the top? 2 and x minus 4, right? So 2 times x minus 4, we factor that out, and what is the leftover? So this is 2 times x minus 4, and this is going to be 5 times x, right? And at the bottom I have 5 times x to the power 1/5. Okay, we're almost done. I'm not going to do anything with that 2 times x minus 4. Now this one, I will distribute this 2, so this is 2x minus 8. But then we have plus 5x, so this is 7x minus 8. And at the bottom we have the same thing. 5 times x to the power 1/5. Okay? Now, what are the criteria? Critical numbers has to come from domain, that is 1. And the other thing is, either the derivative vanishes or it does not exist. Okay, so first, when does it vanish? Now if prime f of x equals to 0, so once again this is a fraction, and the fraction is 0 if the numerator is 0. So this means 2 times x minus 4 times 7x minus 8, this guy is 0. And that means what? That means x equals to, x minus 4 equals to 0, which gives me 4, 7x minus 8 equals to 0, which gives me 8 over 7. Okay? And when does the derivative fail to exist? If my denominator vanishes, right? So that means if x to the power 1/5 is 0, which means x equal to 0. Okay. Now, which numbers among those three are critical numbers? Is x equal to 0 in the domain? Yes, it is. You can evaluate this, right? 0 to the power 450 is 0 times a negative 4 square is 16. 0 times 16 is 0. 4, you can plug in 4. That also makes it 0. You can plug in 8 over 7. So all of them are coming from the domain. Okay? Therefore, all of them are critical numbers of f. Okay? Since x is equal to 0, 8 over 7 and 4 are in the domain of f, the critical numbers, they and the critical numbers of f are x equal to 0, 8 over 7 and 4. So 3 critical numbers. Okay? Alright, so just to rewind these things. A function has a local extrema at a point. If a function has a local extrema at a point, then those points will be critical numbers. But if we have critical numbers, that does not guarantee that it's going to be local extremum. Okay. All right. I'm going to actually end this class just talking about one thing. So we talked about this fact that we have a function that is like this. And how are you going to calculate the global extrema, right? And by extreme value theorem, if our function is continuous on a closed bounded interval, then it definitely has both global maximum and global minimum, right? And the question was, how can we locate those numbers? And the idea was, we'll just compare the values at the endpoints with the values at the critical numbers. Okay? And now we have a tool, an algorithm to find those critical numbers. So we can just evaluate, we can just calculate the global extrema right now. Okay? So that's the last problem we're going to do. So example, find the global extrema of f of x equals to, what is it, 12 plus 4x minus x squared. Notice that's a polynomial, so it's continuous, right? But we also need what? Closed and bounded interval on 0 to 5. Okay? So that's our closed and bounded interval for this problem. Alright, so first, step 1, find the critical numbers. In order to find the critical numbers, we have to start with the derivative. So f prime of x is what? 4 minus 2x, and we can factor out 2, so this is 2 minus x. Okay? Hence, f prime of x equals to 0. That means x equals to 2. Alright? Therefore, x equal to 2 is the critical number of f. Okay, so we know the critical number. We don't know whether that is maximum or minimum or neither, but we don't need to. Okay, we just need to find the global extremum, and for that we have to just compare the values at the endpoints, which is f of 0 and f of 5, and we need to evaluate the function at 2, and we just need to figure out which one is the largest and the smallest. Okay, step 2. Global max maximum is, so this is the maximum among those values at the endpoints, which is f of 0, f of 5, and the values at the critical numbers, f of 2. Okay, so we calculate those values and then evaluate them. So max of, so what is f of 0? If you plug in 0 there, we get what? 12. Okay. What is f of 5? If you plug in 5 here, this is how much? 20, and this is minus 25, so this is negative 5. 12 minus 5 is 7. And what is f of 2? So this is 8. 12 plus 8 is 20. 20 minus 4 is 16. Now what is the maximum among these three numbers? 16, right? So there you go. That's your global maximum. Okay. Similarly, global minimum. Minimum is what? This is minimum of these numbers. F of 0, f of 5, and f of 2. So this is minimum of 12, 7, and 16. And what's the minimum of them? 7. So there you go. Okay. So I know this is a long video lecture, but we just finished one part of the story. Now we know how to calculate global extrema of a function on a closed interval, continuous differentiable function. Yes. So that was not that hard, but we haven't quite finished the story of finding local extrema, right? We have a criteria to figure out where they can happen, right? They will, if there is some local extrema, that will occur at those critical numbers. But having those critical numbers is not enough. It doesn't tell you whether that's it's going to be a local maximum or a local minimum or neither one, right? So we need further analysis. So what do you need? So I will just briefly mention that. So that next time when I will start this topic again, we will know where to start from. So what is the question now? So how to determine whether a critical number gives a local maximum or a local minimum or neither. So that's the question. We're going to leave this question here. I'll actually tell you right now how to figure out that question, but we will not solve the question. The idea is pretty simple. So what is the idea? So let's look at this graph. Let's say this is C, this is D, and this function has a local maximum at C, right? And a local minimum at D. Now notice on the left side of C, this function is increasing, right? As you are giving bigger inputs, you are getting bigger outputs. So on this part, this is increasing. And after it hits that f of C, it starts to decrease, right? Otherwise, it will not be a local maximum. So this is decreasing. Okay. And at D, what happens, on the left side of D, it is decreasing, and after D, it is increasing. Okay. So, this is the summary. So, a function f has a local maximum at x equals to c if f is increasing on the left of C and decreasing on the right of C, right? Similarly, it has a local, minimum at x equals to d if it is decreasing on the left of D and increasing on the right. Okay? All right. It's that simple. It's just this idea. But here is one problem. If you know the graph of a function, from that graph you can actually read the intervals where it is increasing or decreasing, right? But if you have just the rule of a function, say for example sine x squared, where is it increasing or where is it decreasing? How do you know? You cannot know. That's hard, right? So we need to come up with some technique so that just looking at that function and finding its derivative, we can tell whether it is increasing or decreasing. Okay? Now one thing happens, so here is the upshot. Function f is increasing on an interval, let's say a to b. Now here's the thing, if this is increasing, then f prime of x, so this implies, right, if my function is increasing, then f prime of x is greater or equal to 0 for all x in that interval. That we can actually prove, and it's not hard. It's just doing the same thing as Fermat's theorem. Similarly, a function is a function f. Let me just write it on that side. f is decreasing on an interval a to b, if that happens, then f prime of x is less or equal to 0 for all x in AB. Now notice again, this has the same problem, right? You need to know beforehand whether your function is increasing or decreasing, but that we cannot do. As I said, like let's say sine x squared, right? We don't know when it is increasing or decreasing. We cannot actually figure out those intervals very precisely, right? So this one has the drawback that we have to know beforehand whether my function is increasing or decreasing. But if we knew whether my function is increasing or decreasing, then that's it. We can actually figure out whether those critical numbers are local max and local min. That's done, right? But that we can do only if we have the graph. But I mean, we don't have the graph in most cases. Actually, we are going to use this local maxima-minima technique to graph a function. Okay? And as I said, it is not hard to prove these things. I'm not doing this today because I'm telling you why. What you need is something completely opposite to this thing, because we have a really good hold on finding derivatives, right? We have the function, we can find its derivative pretty easily. So once we can find the derivative, then we can actually solve this inequality when this derivative is positive or negative, right? So if we knew that if derivative is greater or equal to 0 implies that function is increasing, that would have been really awesome. And then we can completely solve this problem without any issue. And believe it or not, actually this is an if and only if statement. So if function is increasing, then derivative is positive or 0. That's true. But also if derivative is positive or 0, then my function is increasing. If derivative is negative or 0, then my function is decreasing. Okay. Can anyone tell me why did I draw those other implications in blue? Because in order to prove this direction, we need the mighty mean value theorem. Okay? And that's the twist of this story. Once we know the mean value theorem, then we can prove the reverse direction, and then we have this nice statement. And then we can just find the derivative and solve the inequalities when it's bigger or equal to 0 or less or equal to 0. And that's it. Okay, then we can find the critical numbers, and also we can determine whether those critical numbers give us local maxima or local minima. So that will be the end of this story of Extrema. But to end this story, we first need to talk about mean value theorem, and that's the content for next video. After that, we'll come back to this story of Extrema and finish that. But until then, bye.